we're going to start in packet 1 here. The first several pages are reference material. So we have an integration formulas sheet. Most of these you don't know yet, so you might just keep it in the back of your head that this is here for when we start doing more integration. This is an integration technique. You can bring these reference sheets with you to the test in addition to your 1 page of notes, these pages at the front. Except for this, the strategy guide for differentiation is no longer allowed on tests. So now that you are successful Calculus 1 completed students, you should know how to do all of these by heart. Cliff Notes version of Calculus 1. All right, class 1. Review of differentiation. So project 1 and quiz 1 are assigned today. I just handed out project 1. Quiz 1 isn't printed yet, but it is in Moodle if you want to get started on it. But it covers more than just the review, so you also might want to wait. Okay, so we're going to start off the semester with our first classroom voting question. So I'm going to have you, actually, you know what? So I'm going to have you work through the classroom voting questions. I want you to discuss in your groups, or you can write down the answers and then compare with your group mates the answers to the classroom voting questions. There are 7 or so. So if you've jumped out of a helicopter, the graph of your speed as a function of time from the time you jumped out of the plane would be what? A, B, C, or D? Okay, so I've got an A and I've got a C. So do we all agree that your speed is increasing? So you go faster and faster and faster as you fall. Okay. So your speed would be increasing because you're going faster and faster. Now, how is it increasing? Like the first 10 feet that you fall, you gain a certain amount of speed, right? And then the second 10 feet that you fall, you gain another certain amount of speed. Over which 10 feet do you gain more speed? The second? Why over the second? Okay, so if we're taking air resistance into account, then you're actually fall faster at the beginning, right? You're going faster and faster and faster as you fall, but at some point, air resistance is going to equal out. Going to resist the force of gravity, and you're actually going to continue falling faster and faster and faster, but until you reach terminal velocity, which means then you're going to be falling at a constant speed. Right? So you're going faster and faster and faster, but then you're slowing down. But that you're not slowing down, but your rate of change is slowing down, which means you're concave down. So increasing concave down with air resistance, right? If there were no air resistance, what would the graph look like? Would it be A? What does the acceleration do to gravity? That's your position. Your position function is quadratic, right? Yeah. Yeah, it's 32 feet per second, or 9.8 meters per second, which is a constant, right? So your acceleration is a constant, which means that your speed has a constant rate of change. So it actually would be none of these. Right? Concavity tells you how the rate of change is changing. If it's concave up, that means your rate of change is increasing. Concave down, your rate of change is decreasing. But in the case of gravity, the rate of change of speed is acceleration, and that's constant. So your speed would be increasing, no concavity. It would be increasing linearly. A little bit of a trick. All right, what if we replace the word speed with the word velocity? How would my answers change? I don't know, I'm asking you. Yeah, so velocity has a direction. So down would be negative. So if you're going faster and faster in a downwards direction, your velocity would be negative, bigger and bigger negative numbers. So think of a number line. If you're going bigger and bigger negative, what's happening to the value of your velocity? It's decreasing. Yeah. So we would actually, velocity is decreasing because it's becoming more and more negative. Okay, unrelated to the previous two questions. True or false? A local maximum of f only occurs at a point where f prime equals 0. Why is it false? It can also be at a place where the derivative is undefined. Right, so for example, you could have a graph that looks like this. It's got a local maximum right here, but the derivative is undefined there at that corner point. All right, true or false? If f double prime equals 0, f has an inflection point at a. F double prime of a equals 0. Did you say true, Ed? Why did you say true? Mm-hmm. Yeah, so if f double prime is 0, you're saying that that means that we had a change in, f double prime had a change in sign, right? And when the second derivative is positive, concave up, second derivative negative, you're concave down. So when f double prime is 0, you had to have changed from positive to negative, so there's an inflection point.
Wouldn't it be though if there was like a straight line graph, would that be f double prime of 0?
Yeah, so that's, I mean, there was a flaw in my argument, right? It's not necessarily true that if a function equals 0, that it changed from positive to negative there. Right? So for example, right, if f of x equals 3x, right? F prime would be 3, and f double prime would be 0. So that means that f double prime is 0 everywhere. Does it have an infinite number of inflection points? It's constantly changing concavity? So here I would say, well, that means that f double prime of 4 is 0, right? Double prime of anything is 0, but I don't have an inflection point at 4. In fact, I have no inflection points because the graph of f is just a line. So this is not necessarily true. A would be a candidate for an inflection point, but not necessarily an inflection point. In order for there to be an inflection point, f double prime would have to be 0 or undefined. But being 0 or undefined does not necessarily mean there's an inflection point. We say it's a condition that is necessary to have an inflection point, but not sufficient. Necessary, but not sufficient. So this would be false. And this one was false. All right, f of x equals ax plus b over x. What are the coordinates of the critical points of f? How do we find critical points? where the function equals 0?
Where you set x to 0, or at least set the function equal to 0 and solve for x.
Close. Set the derivative equal to 0 and solve for x. Yep. It's places where the derivative equals 0 or the derivative is undefined. Right? So first we should find the derivative. So the derivative of ax would be a, and the derivative of b over x. So sort of the easiest way to approach that, you could use a quotient rule, right? But the numerator is just a constant, so you're going to get a bunch of zeros when you do the quotient rule. Or you could think of b over x as b times x to the negative 1 and use the power rule. So you'd end up with negative bx to the negative 2, which would be a minus b over x squared. Then you set that equal to 0. Places where this equals 0 or this is undefined. So that would be when a equals b over x squared. So x squared equals b over a. Just multiply both sides by x squared and divide both sides by a. And so you get x equals plus or minus the square root of b over a. And also we have to take into account places where the derivative is undefined. What x value makes that undefined? X equals 0. Okay, so we've got 3 critical points. Plus or minus radical b over a, and 0. So we've got b and c. Did you guys come up with c? Yeah, good. Okay, one more. F of x is this quadratic, negative 3x squared plus 12x plus 7. We want to look at the quadratic only on the interval negative 2 to 4. Where does it have a global maximum? The highest y value on that interval. Okay, so where could global maximums happen? Where the derivative equals 0, or, say that again? The end points of the interval, yeah. So we want to find f prime equals 0, or f prime of x undefined, right? Because those are also critical points. So you could have a global maximum at a critical point or at an endpoint of the interval. All right, so f prime would be negative 6x plus 12. Negative 6x plus 12 is never undefined, so I'm just going to set it equal to 0 and solve it. And I get x equals 2. So then, how do I decide which of these points, which of these x values is the location of a global maximum? And what? Yeah, plug those values into the function f, and the one that gives you the biggest value is the global maximum. So I have to take f of negative 2, f of 2, and f of 4. Okay, so let's see. Negative 2 squared is positive 4, and positive 4 times negative 3 is negative 12. 12 times negative 2 is negative 24, plus 7. So it's negative 36 plus 7 is negative 29. Okay. Now I plug in a 2. 2 squared is 4 times negative 3 is negative 12. 12 times 2 is 24 plus 7. So negative 12 plus 24 is 12 plus 7 is 19. And then finally we plug in 4. 4 squared is 16 times 3 is 48. 12 times 4 is 48. Negative 48 plus 48 is 0, plus 7 is 7. So which x value gives me a global maximum? A 2. Yeah, the 2. What is the value of the global maximum? 19. Good. So this would be x equals 2, is the location of the global maximum. All right, you can work on the challenge throughout the course in the packets. Sometimes I give you, a few problems to work on in your groups. If you finish them, there's usually a challenge problem that you can work on, but you don't have to. So you can do that at some point. We'll jump down to number 8. All right, so calculus 2. We're going to take 2 days only to review. Today, derivatives. Next class, definite integrals. The course is roughly divided into 3 parts. Part 1 is evaluating integrals, techniques of integration, how to find an integral. Just like a lot of Calc 1, a big chunk of Calc 1 was how to find a derivative. All right, so the next chunk is then applications of integrals. So we're going to talk about geometry and physics and economics and probability. And then part 3 is sequences and series. How do you add up an infinite list of numbers? How much is 1 plus a half plus a fourth plus an eighth plus blah, 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 blah? And what does this have to do with calculus? All right, so our quick review on derivatives. Who remembers the original definition of a derivative? Yes, slope of a tangent line. And how did we calculate it? Let's write that down. That's a good. How do we originally calculate it before we had any shortcut rules for differentiation? Using a limit, yeah. We would calculate what was called the difference quotient. Right, and that is the slope of a secant line, right? So here's someplace x, move some distance to the right h, and you'd land at x plus h, right? And if I have some curve on here, if I connect the points at x and at x plus h and find the slope, that's this formula. F of x plus h is the y value here. F of x is the y value here. Change in y over change in x. It's the slope of that secant line. But then what we do is we let h go to 0. Right? We let this distance between x plus h and x, these 2 points get closer and closer and closer to each other, and that secant line becomes closer and closer and closer to a tangent line at x. So this was our definition. What were some of the interpretations of derivative? Interpretation or application? Yep, velocity. So position, velocity, acceleration. So we used derivative to talk about motion. What else? Anything you can think of? How about sort of more general interpretation of the derivative? Rate of change, yeah. Yeah, so velocity is a rate of change of position with respect to time, but you can use a function to measure all kinds of things other than position, and we interpret the derivative as a general rate of change. All right, how do you find or estimate a derivative if you're given a table of values? Actually jump to the next page here. Here's a little table of values. How would I estimate f prime of 2? Take a difference quotient. All you can do is estimate, yeah. So you might go on either side. So you might do f of 3 minus f of 1 over 3 minus 1, slope of a secant line, to estimate the slope of the tangent line. So again, these are all estimates, and it's hard to know which estimate is going to be the best. This particular one, we'd end up doing 9 minus 1 is 8 over 2, which is 4, right? Or you might do estimate by just using x equals 2 and x equals 3, or x equals 1 and x equals 2. That would be 5. All right, how about if you're given a graph? Here's a graph of a function. How would you estimate or find f prime of 2? Yes. Yeah, so we could go over to 2, draw a tangent line to the curve at x equals 2, and then find its slope. So to find the slope of this line, if you're going to do this graphically, you probably should use a ruler, draw a nice straight line, and then find 2 places where it crosses. Like that looks like a good point at 1, 0, and then try to find another grid line where that looks like it crosses there at 3, 8. So then find the secant line, or find the slope of that line, which is a tangent line. So the slope is change in y over change in x, so this would be 8 minus 0 over 3 minus 1, which is 4. All right, and how about if you have a formula? If you know that f of x equals x squared, what's f prime of 2? 4, yeah. So first you find f prime, find a formula for f prime, which we said was 2x. Then you plug in your 2, so you have 2 times 2, which is 4. All right, so I've got 4 functions here, and I would like you to find dy, dx for each of them. So a little review. You can work on them individually or discuss in your groups. You have the answers, so you can check, and then we'll go over them in a few minutes. So most people are either finished or just finishing up. So let's go through how to do these. For 5 to the 3x, what is the derivative of 5 to some stuff? Derivative of 5 to some stuff. Yes, so 5 to the stuff times the ln of 5. So that's the general rule for a to the x is a to the x ln a. So we have some stuff here, so it's going to be five to the 3x times the ln of 5. Then we also have to apply the chain rule here because it was 5 to some stuff. So we have to multiply by the derivative of the stuff, which is 3. Now, is there any, can I simplify this any further? Could I write the ln of 15 or maybe 15 to the 3x? I can't do any of those things. That's the best I can do. All right, so for part B here, what's the overarching rule? The first thing that we have to work on. It's a product, yeah. 7x minus 4 cubed times arctan x. So I'm going to use the product rule here. So y prime, remember, is first times the derivative of the second plus the second times the derivative of the first. So first is 7x minus 4 cubed. So you don't have to do anything. You just write down the first function, 7x minus 4 cubed, times the derivative of the second. What is the derivative of arctan x? You got it, yeah. 1 over 1 plus x squared. So it's first times the derivative of the second plus the second, we just copy it down, arctan x, times the derivative of the first. What is the derivative of 7x minus 4 quantity cubed? Yep, so we had some stuff cubed. So we apply the power rule to the stuff, bring the 3 down, stuff squared. But then you still have to multiply by 7, the derivative of the stuff. Stuff is 7x minus 4. Its derivative is 7. All right, can I simplify that? What could I do? Into the numerator of that fraction, yeah. So I could... Oh, yes, yeah, so I could factor 7x minus 4. I guess, yeah. Did I do that here? I didn't. Yeah. With complicated derivatives, my general rule of thumb is if you can simplify it in a step or two, you should do it. If it's going to take 19 steps, you should not do it. It's not worth the trouble. So the only thing that I might do here is look at those two guys and write them as a single fraction, just because it would take up less space. And then in the second term, I would multiply the 3 and the 7, make it 21. So just to make it look a little neater without doing a huge simplification. The important thing is that we're reviewing the rules of derivatives. All right, so for C, the ln of some stuff. What's the derivative of ln of x? 1 over x. Good. So if I want to take the derivative of the ln of some stuff, it's 1 over the stuff times the derivative of the stuff. So y prime here is going to be 1 over this stuff, e to the x squared plus cosine x, then times the derivative of the stuff. Okay, so what is the derivative of e to the x squared? Yep. So the derivative of e to some anything is e to that thing, but then apply the chain rule, take the derivative of the stuff. And then what's the derivative of cosine x? Negative sine x. There we go. All right, and then D, caught a lot of people forgetting how to do an implicit differentiation. So you could either solve this equation for y, but then you'd have two equations, a plus and a minus square root, and you'd have to take two derivatives. Or you can use something called implicit differentiation and take d dx of both sides. So we take the derivative of x squared plus y squared, and that will equal d dx of 2x. Oops, sorry, that's a minus. All right, so what's d dx of x squared? 2x. What is d dx of y squared? 2y, y prime. Good. So y is really a function of x, so we take the derivative of y squared and we get 2y. Then you have to multiply by the inside for the chain rule, y prime. And what's d dx of 2x? 2. then we just solve for y prime. If you divide everything on both sides by 2, oh, I didn't even simplify it here, but you can cancel out all the 2's. And then you'd end up with y prime equals 1 over, so that would be 1 minus x over y, negative y. All right, so that finishes our review of derivatives. For homework, you should review Chapter 3 as necessary. Chapter 3 is all the derivative shortcut rules. Due from the 6th edition, I have the problems here. If you need 5th edition problems, they're in your syllabus. These are the things that you should be able to do after class and doing the homework. To prepare for next class, you might want to read Chapter 5 ahead of time. And then other things to do is to start working on Project 1, to do on Class 9, and start to look at Quiz 1. It's a quiz on Classes 1 through 5, due on Class 6. Again, I don't have it printed yet, but it's in Moodle if you want to look at it. You can use whatever resources you want on a quiz, except for the help of another person. So you can use class notes, book, internet, whatever. Correct. Yeah. Make sure you read all the course syllabus. Let me know next class if you have any questions. If you haven't already, you should buy a copy of the textbook. And if you don't have one already, you should just obtain some kind of graphing utility and visit the Moodle site. Check that you can view all the information there. And that's it. I will see you Wednesday.